So now we're going to look at some stoichiometry problems that involve solutions, but that also involve having to determine the limiting reactant. So hopefully you remember that when two reactants are combined, one of the reactants determines how much product will be made because it's going to run out first. And that's the limiting reactant. And the other one is called the excess reactant. So when you're doing solution stoichiometry questions, you may also have to figure out the limiting reactant before determining how much product can be made. And just like before, this occurs when you're given information about both reactants. So let's look at some examples. So the first example, find the mass of aluminum hydroxide. So that's the precipitate in this double displacement reaction. So find the mass of aluminum hydroxide that precipitates when 20 mils of 0.050 mole per liter aqueous aluminum sulfate is mixed with 30 mils of 0.0185 moles per liter of aqueous calcium hydroxide. So we've been given volumes and concentrations for both reactants. So we need to figure out what the limiting reactant is before we can figure out what mass of the product is created. So there's a couple different ways we can do this. So for this sample, I'm going to use one way, and then with the next sample, I'll use a different way. So for this one, what I'm going to do is determine the moles of each reactant that's available. So I'm going to use the volume and the concentration to calculate moles. I'm going to do that using the conversion factor method, but you could also use the formula, right, that N equals C times V. So find the moles of each reactant available. So for aluminum sulfate, 0.02 liters. So remember, we need to convert that milliliters to liters, times 0.0150 moles in every 1 liter. So we've got 0.000300 moles of aluminum sulfate in the reaction vessel. So then we do that same calculation for calcium hydroxide, 0.0300 liters times the concentration, 0.0185. So this tells us that we have 0.000555 moles of calcium hydroxide in the reaction. So that's what we start with. So then we're going to choose one of those, and we're going to use the mole ratio to figure out how many moles of the other one would be required to completely react. So if we choose aluminum sulfate, we're going to use the mole ratio, which is 3 moles of calcium hydroxide for every 1 mole of aluminum sulfate. And when we do that calculation, we get 0.000900 moles. So that's the amount of calcium hydroxide we would need if we were going to be able to react all of the aluminum sulfate. And we do not have even close to that much, right? We've only got 0.000555 moles, so that's quite a bit less. So what that tells us is that the calcium hydroxide is the limiting reactant. So now that we know that the amount of product is going to be determined by the amount of calcium hydroxide, we can take the moles of calcium hydroxide that are present and use that to figure out the mass of precipitate that's formed. So we take that 0.000555 moles of calcium hydroxide. We're going to use the mole ratio to find out how many moles of aluminum hydroxide would be created. And then we're going to use the molar mass of aluminum hydroxide to figure out the grams that would be created. So when you calculate that out, you get that there are 0.0289 grams of aluminum hydroxide precipitated when those two solutions are mixed. So now let's look at another question. Find the concentration of copper 2 nitrate in a solution made by mixing 0.25 grams of the copper metal with 50 milliliters of 0.125 mole per liter aqueous silver nitrate. So we need to find the concentration of copper 2 nitrate, which means we're going to need the moles, so we can then divide by the volume to get the concentration. So for this one, what we're going to do is we're going to determine the moles of copper 2 nitrate that can be made by each reactant. So if each reactant reacts completely, how much could be made? And whichever one produces the least, that's what is actually produced. So we have 0.25 grams of copper. We use the molar mass of copper to get to moles of copper. And then we're going to use the mole ratio to figure out how many moles of copper 2 nitrate. In this case, it's just a 1-to-1. So that tells us that if all of the copper reacts, we would have 0.0039339 moles of copper 2 nitrate. So then we find out how much copper 2 nitrate we'd have if all of the silver nitrate reacts. So in this case, we have a solution, right? So we start with the volume, which we've converted to liters. We're going to use the concentration to figure out how many moles. So now we know how many moles of silver nitrate we started with. Now we're going to use the mole ratio to find out how many moles of copper 2 nitrate could be made. In this case, the ratio is 1 copper 2 nitrate over 2 silver nitrate. So when we calculate that out, we find that if all the silver nitrate reacts, we get 0.003125 moles of copper 2 nitrate. So the silver nitrate makes less than the copper. So that means that that is the actual moles of product that are made, because the silver nitrate is going to run out before all the copper can be used. Next, we would calculate the concentration. We now know the moles of copper nitrate that would be made, and we divide by the volume, and this was a reaction in 50 milliliters. So we divide by 0.0500 liters, and we find that the concentration is 0.0625 moles per liter. So those are two examples of possible stoichiometry problems that bring in the idea of limiting reactant. Just like in previous questions with limiting reactants, you can also get asked questions about the excess. So how much of the excess remains, what is the concentration of the ions remaining in solution. So there's lots of different variations on questions that you can get once you add solutions into the mixture of stoichiometry problems.